Now let's move to the third part, diversity detection. In this part, we mainly focus on detect data, okay? And we want to discard diversity data if we found something should be come from the attackers, okay? So we want to discard them and we are not considered to make any prediction on that, okay? So in this line, adversary detection, the first work might not first work, but the first representative work is detecting adversary examples from artifacts. And it shows that the three possible situations of the adversary example X star lies in the data manifold. Okay, the first one is like this figure. The second one is adversary data is really in the other manifold. Okay, but it's not in the manifold, but it's near to the other manifold. The last one is this one. It's a nearby to the submanifold. Okay. And given the intuition that adversary samples lie off the true data manifold, we can look at this figure. Although adversary data is not in the original manifold. Okay. So in this work, the authors devise two measures that can be used to detect adversary examples. The first one is kernel density. The second one is Bayesian uncertainty. Okay, it's very useful to help us to identify, okay, if this point is in the manifold of other points. Okay. After this work, Ma found that the previous work might not work very well, especially for kernel density. It's not effective. We can look at this figure. In this figure, okay, both data size are different, okay? And we want to say, okay, what's the value, what's the point value in this cross area and this star area, okay? We can find that for previous method, okay, the Km is one measurement, Kd is another measurement. They have same value for that, okay? However, it's obviously like the second one, the star should be considered as some outliers, okay, instead of same value, okay, compared to this one, okay. So in this work, they consider the local intrinsic dimensionality to help us identify, okay, if the one point is really lie off of a manifold of data point we are considering, okay. And you can say based on this metric lead LID, yeah, it's very different. The value is very different, and higher value means that okay, it's far away from the manifold. After this work, and researchers also consider and propose a lightweight Bayesian refinement for detecting adversary test samples. Okay, so given pre-trained deep network, the library converts its last few layers to a Bayesian and use uncertainty as a metric. Okay, uncertainty as a metric, and to train a model to detect if this one is adversary or benign or nature example. Okay. So when this adversary detection, this field develops, and we found that there is some cautions in related works. It's a two-symbol test is unaware of adversary attacks. Two-symbol test is a statistical tool to help us identify if two sets of samples are from same distribution. Okay, so we have nature question. Are nature and adversity are really from different distributions? Okay, and in this work, we give the affirmative answer. Yes, they're from different distribution. And the previous work, they did something wrong when they use two-symbol test. Okay. So previous use MMD test. MMD is just one of representative two-symbol test. On the purpose means three key factors. Factor one, limited representation power of Gaussian kernel. Okay, they use Gaussian kernel as a very limited power in the literature, in the two-symbol testing literature. Factor two, the overlook of optimization of the used kernel parameters. So in Gaussian kernel, we always have parameter called a bandwidth or length scale, okay? And it's very important to ensure this kernel effective to select the proper kernel parameters. However, in this work, in the previous work, they didn't consider that, the overlook the optimization for the used kernel parameters. The third factor, yeah, they consider non-ID they didn't consider non-IID case. Sometimes the adversary data might be non-IID, and it will break basic assumption of MMD test. So in this work, also propose the semantic aware maximum mean discrepancy. Okay, and why we consider the semantic aware? We can look at this figure. From this figure, we can say the nature data indeed have different patterns compared to adversary data. Okay, this is the TSNE of the second to last layer of the well-trained network. Okay, you can see it's very different. We can definitely tell nature are from different distribution from all this adversary data distribution. Okay. So it also mentioned us we can use the second to last layer features, okay, to help us do the two-summer testing task. So here is how we design the kernel architecture. Yeah, and we consider the 5P here just the neural network except for the last layer, okay, except for last layer. So it's a feature extractor of the network. And we just use the Gaussian kernel and to compute its similarity, okay? So in this kernel architecture, it follows previous work. We only have three parameters, the epsilon zero, the bandwidth for this kappa, and the bandwidth for Q, okay? So we only have these three parameters. And then we can just optimize these parameters based on the asymptotics of the proposed statistics and finally detect the adversary examples. Okay. And based on that work, recent research also considered to use more advanced statistics to help us identify the adversary data. Okay. Like I said in the adversary purification, the score is very important because diffusion model is very successful. Okay, and the main technique, statistical technique used in diffusion model is called score. Okay, it's log density, first derivative of log density. Okay, and in previous work, they already found that the norm of this score can somehow help us identify adversary data or nature data. Okay, but it's not strong signal. So in this work, we'll consider perturb our data. Okay, so when we have the data, when we have one image, okay, we can always perturb this image by adding the noise. Okay, by diffusion process. For each image with some noise, we can compute the score norm. We can compute score norm, okay. And then we found that for nature data, the score norm, perturbed score norm is always lower, it's relatively lower than the adversary data, okay. It motivates us to consider, okay, we can just use this perturbed scores to help us identify if this image is adversary or nature. Okay, so there's a main pipeline for this method. For different images, we will always perturb this image and get a lot of perturbed images here. And then we just compute the score norm for each perturbed image and get average on that. So it's this expected perturbation score. Okay. And finally, we find that it's very useful to help us identify if this one is adversary example or if this one is nature example. So in the second work here, we found that a lot of papers, they are consider detect adversary data, the adversary data sample-wise, okay? But in some work, like testing work, it's we are consider detect those data using batch instead of the instances. So we have a question here. Can we do a single instance-based adversary data detection perfectly? Okay. The answer is no. In our recent work, we found that adversary data and nature data are too close to be perfectly distinguished. And in this paper, we provide an impossibility theorem to support this answer. And this answer also tells us if we really want to ensure our system is adversary robust or adversary safe, it's always good for us to consider to do detection batch-wise, okay? Because the distribution discrepancy between adversarial data and nature data is very clear. It's true. So as long as we have a powerful two-to-one testing method or statistical testing method, we can say, okay, this batch contains some adversarial data. Okay. And it can be and has very nice theoretical guarantee for that. Okay. So that's that's all for today's tutorial. And welcome to send your question to my email. Thanks for the listening.